Okay, so here's where we left off. We were talking about significant figures and what to do with them when we do mathematical operations. We talked about multiplication and division, and we moved on to adding and subtracting. And so here's a couple of examples for adding and subtracting. So the question says, perform the calculations to the correct number of significant figures. The first thing to do is get out your calculator and do the math. 2.18 plus 5.621 plus 1.5870 minus 1.8 equals. So what color are we? White. So my calculator is showing me 7.588. Did anybody else get that? Okay. I recommend you do calculations twice because it's so easy to screw up on punching buttons. So then what we have to do is we have to decide how many significant figures should this answer have. This is adding and subtracting, so we're not counting number of significant figures, we're counting number of decimal places. Where is the largest uncertainty? And so if we look at this first number, we see that we've got 2 decimal places. This one has 3, this one has 4, and this one only has 1. This has the largest uncertainty. There's uncertainty in the tenths place. And so that's going to limit our answer. So we're going to keep only the tenths place. So I'm going to write down what my calculator says, and then I'm going to round it off because this is the final answer for this problem. So we're going to keep that tenths place. We look at the next digit that's being discarded. The first one, it's an 8. We don't care about the other 8. We just look at that first 8. We say, okay, that's 5 or greater. We're going to round up. Our answer is 7.6. Okay. Stray marks. Okay, so the next one, 7.876 minus 0.56 plus 123.792. My calculator is showing me 131.108. Anybody else get the same number? Okay. So again, we're going to go looking at, where am I? There I am. We're going to look at where that answer came from. The first number had 3 decimal places. The second one had 2 decimal places. The third one had 3 decimal places. This middle one has the fewest number of decimal places, 2. So that limits our answer to 2 decimal places. We have to stop there. So again, we're going to look at the next digit. It's 5 or greater. We round up, and we're going to call this 131.11 as our final answer. Any questions? The rules for adding and subtracting are different than the rules for multiplying and dividing. Sometimes we have problems where we've got multiplication, division, and adding and subtracting mixed together. And those get a little more complicated because we have to look at the rules separately for each type. So if there are parentheses, do those steps first. You have to be careful with order of operations. Okay, and that's a math topic. I'll address that as it comes up, but I'm not going to teach you order of operations all over again. So then, in those individual steps, you're going to find the correct number of significant figures, those intermediate answers. You're not going to round them off, though. And so that's where underlining helps. Underline that uncertain digit, the first uncertain digit, the one we're keeping. Leave the others in there for the calculation. Then finish out the remaining steps, get your final answer, and then go back and look at the individual pieces and where things came from to figure out how many significant figures you have. So here, let's do this problem. So we have multiplication mixed with subtraction. The subtraction's in parentheses, and so we're going to do that first. And we're going to look at the result of that. So 782.3 minus 451.88. I'm actually going to write that down, but I'm just going to leave it in my calculator. So my calculator says 330.42. Now I need to address how many significant figures, if that was the final answer, how many should it have? Subtracting again. So we look at the individual numbers that it came from. So this one has 1 decimal place, and this one has 2 decimal places. This result here then should have 1 decimal place. So I'm going to underline the 4, just because I figured it out, and I'm going to make a note to myself. That's the last significant digit. Now I'm going to do the rest of that math. 3.897 times this number. I have this number in my calculator right now, so I don't have to type it in again. I'm just going to multiply by that first number, 3.897. Okay, and for space, I'm going to write that up here. Here's the answer that my calculator gives me. Oh my goodness. 1287.64674. Anybody else get that? Good. Okay, so we have to address how many significant figures does that answer have? Well, we're going to look at where it came from. It came from multiplying this number and this number, right? So this first number has how many significant figures? 4. Because this is multiplying now. We're not looking at decimal places. We're looking at number of significant figures. The first one has 4, and the second one has, well, it shows 5, but I underlined the 4, meaning that's the last one we're keeping. So they both have 4 significant figures. That means in our answer we're going to keep 4 significant figures. So over here, the 1, the 2, the 8, and the 7, that's the 4th digit. So I'm going to round to the ones place. The next digit is 6, that's 5 or greater, I'm going to round up, and so my final answer is 1,288. That make any sense? Any questions about that one?
I have a question.
Yes.
So if one of them had 3 and one had 4 sig figs, you would go with the one with 3?
Yes, if those two numbers, instead of having the same number of significant figures, if one had 3 and one had 4, the rule for multiplication says that we would use the one with the smaller and we'd go with 3. Yeah. Any other questions? Let's do part B. So again, we're going to do the part in parentheses first. So 4.58 divided by 1.239 equals. And we're going to write that down, and that's a big long mess. 3.696529459. Yikes. And then we look, where did this number come from? Well, it came from 4.58, which is how many significant figures? 4.58? 3 sig figs. And this one has 4. So the result of that division should have 3, the smaller number. So this is where that number ends, in that third one. So 3.69, if we were all finished, we'd round it now, but we're not done with our calculation. So I have that number in my calculator still, and then I'm just going to go ahead and do minus 0.578 equals, and then I'm going to write down what that's showing me. 3.118529,459. Okay, that's way too many significant figures. But now we can look at the two pieces that that number came from. So it was this, I have a hard time with this pointer. It was this number which had how many decimal places? 2. Remember, we're only paying attention up to the underlined digit, because the rest of that's garbage we're going to throw away later. So this one has 2 decimal places. We're subtracting, so we're looking at decimal places, not sig figs. And we subtracted this number that has how many decimal places? 3. The first one had fewer decimal places, 2 decimal places, and so then in our answer we're going to keep 2 decimal places. We look at only the next digit. It's an 8. We need to round up. 3.12. And on your lab work, which is the only turned in stuff with written answers that I see, it's really helpful if you put a box around your final answer. Because, sometimes when we do these problems, I'm scribbling on the board here. There's all this scribbling around, and sometimes I have to search around to look for your final answer. So a box around it's really nice. Question?
On A, the 1288, you change on the calculator worksheet, what I would do if I had a number like this, change it to scientific notation.
Yeah, changing to scientific notation is always a good idea. And we'll see in the future where sometimes we'll have a really big number that we have to round off, and then we can end up with some problems, because what would happen if we had to round 1,287 to 2 significant figures? Would we call it 13? No. Hey, I'm going to buy your really, really expensive bicycle from you. It's worth $1,287, but we're just going to round that off and I'll give you $13. That wouldn't be good, would it? So it's always a good idea to use scientific notation, because then we don't get into problems where we round numbers off and change their values. Scientific notation is always acceptable. You only have to use it if the problem specifically says express your answer in scientific notation. Good question. Any other questions? Okay, so we're going to go on and talk about the units. We talked about some numbers and how to write them down and what to do with them and keep track of precision and stuff. Now we're going to talk about units and the importance of units. Here's a great sentence from your book. When my son was 7, he walked 3. And when he was 4, he threw his baseball 8 and said his school was 5 away. Does that make much sense? No. You're like, what? What are you talking about? It's like going to McDonald's and saying, I'd like 2. And they say, oh, you want meal number 2? No, I want 2. And they're like, 2 what? They don't know what, okay? A number without a unit, when it's a measurement, doesn't mean much at all. And so I'm going to really hammer on you guys, always write the units. So what they meant with that sentence is, when my son was 7 months, he walked 3 steps. And when he was 4 years, he threw his baseball 8 feet and said his school was 5 miles away. And that makes a little more sense. Units make all the difference. There's 2 main systems of units that are in use: the English system and the metric system. In this country, we use the English system. The English don't even really use the English system anymore, but I don't know, we're just kind of stuck on it. We give lip service to the metric system. They said, I remember back when I was a kid, oh yeah, we're switching to the metric system. Still hasn't happened. Although it's creeping in. Soda is sold in 2-liter bottles. That's a metric unit. But in science, we use the metric system. Technically, it's the international system of units, which is also known as SI units. And the reason it's SI and not IS is because it's from the French, and they reverse their nouns and their adjectives. As far as I'm concerned, the SI system and the metric system are the same. They're interchangeable. There are very subtle differences, and we're not going to get hung up on what they are, so I'm not going to test you on those at all. These are basic units that are used in the SI system. They are related to the metric system units. So we have different quantities that we measure. One of them is length. For length, the standard unit is the meter. You need to have a clue about how big a meter is. My meter stick is missing. A meter is roughly the same size as a yard. A yard is 36 inches. A meter is a little over 39 inches. But just to have a clue of how big a yard is. And then here it tells you how they've defined what a meter is. I won't test you on that either. The standard unit for mass is the kilogram. A kilogram is about 2.2 pounds. So it's twice as big, but they're in the same ballpark of size. And that is a picture of the official kilogram. Now in chemistry, we tend to use the unit gram more often because it's smaller and more useful to us. Standard unit of time is familiar, it's the second. That's the same in both systems, and that's how they define what the second is. So let's talk about mass. The kilogram is a measure of mass. A pound is a measure of weight. Mass and weight are not the same. Mass measures quantity of matter, how much stuff there is in an object, and weight measures the gravitational pull on that object. So weight is actually a unit of force. And that's going to change if the gravity changes. So if you weigh something on Earth and then you take it to the moon and weigh it, it's not going to weigh the same. But its mass will be the same. Because when you take it to the moon, it didn't lose most of its molecules. They're all still there. It has the same mass. So in science, we use the term mass, but we sometimes say, oh, go weigh that. Well, as long as we stay on the same planet, anybody planning to leave the planet this semester? No, I'm not. I'm not planning to ever leave the planet. As long as we stay on Earth, the gravitational pull is going to be the same, and so we don't have to worry too much. But there is an important difference. So the gram is another unit of mass, and that's what we use in chemistry. What's wonderful about the metric system is that it uses prefix multipliers to change the size of the unit. We want to use units that are similar in size or smaller than the quantities that we're measuring. If I want to measure how wide my calculator is, what unit might you choose to use? You might measure that in inches, right? Because that's what we're more familiar with. Would we measure this in miles? That'd be pretty ridiculous, wouldn't it? We use a unit that's similar in size to what we're measuring. And so we need lots of different units because I would not want to measure the distance between my house and Fresno City College in inches. That would be really, really annoying. We measure a distance like that in miles. So in the English system, we have inches and feet and yards and miles, and the relationships between them are all different. 12 inches in a foot, 3 feet in a yard. I think it's 1,760 yards in a mile. It's, a really kind of random number, right? In the metric system, everything is powers of 10. And so we use the prefix multiplier that's going to make the unit the size that we need it to be. So these are some of the prefix multipliers for the metric system. There's actually a name for each factor of 10, and I asked you to memorize some of these, okay? I asked you to memorize the ones that we're going to run into most often. So each of these, we have the name, like deci, and it has an abbreviation or symbol. And here capitalization counts because mega is capital M and milli is lowercase m. If we put mega in front of a unit, it multiplies it by 1 million and makes the unit bigger. So a megameter is 1,000,000 meters. And if we put milli in front of it, it's 1/1000th, 0.001 meters. It makes the unit smaller. So if we have something very small to measure, we'll measure it in millimeters so that our units are nice and small like the thing that we're measuring. So you need to remember, I think it was, I can't remember if I put mega on there, mega, kilo, centi, milli, micro, and I think I asked you to do nano. Okay, you need to know the name of the prefix, you need to know its symbol. We've got 3 M's here. We've got mega, which is a big M, a capital M, makes it bigger. Milli is a lowercase small m, that makes the unit smaller. And then we have another M, and we ran out of English M's. So we're using a Greek M, a mu. It's like a U with a tail on the front. And that's even smaller than micro. And then you need to remember what it multiplies by. So this is the decimal form. Personally, I find it hard to keep track of all those zeros. And here's the exponential form. So nano means 10 to the minus 9. Mega means 10 to the plus 6. Okay, I did this yesterday at COS and I realized I don't like how they did this example, so I'm changing it. Come on. So I changed the exponent. So if you printed those out in your notes, change it to a minus 9. So here's an example. A short chemical bond is about 1.2 times 10 to the minus 9th meters. Which prefix multiplier should you use to have a unit that's similar in size to that bond? Well, let's go back and look at these prefixes. Which one is close to 10 to the minus 9? Nano. So we're going to use nano. So here we have 1.2 times 10 to the minus 9. Well, nano means 10 to the minus 9. And that's meters. So what I'm going to do is instead of writing 10 to the minus 9, I'm going to write its abbreviation, n. So this is 1.2 nanometers. Okay, that's how the metric system works. Instead of writing times 10 to the minus 9, I write nano. And we all understand that nano means 10 to the minus 9. Any questions? Let's just do another example. What if we had 3.5 times 10 to the 6th grams? What would be a more convenient unit to use? Well, let's look for a prefix that means 10 to the 6th. Remember which one that is? Mega. So mega, capital M, means 10 to the 6th. So this is 3.5 megagrams. And some of these prefixes we hear in everyday life. Have you heard of a megabyte? A megabyte is 1,000,000 bytes, computers. A gigabyte drive, a terabyte drive, those are metric prefixes that mean 10 to the, gigas, I think 10 to the 9th, and tera's 10 to the 12th. I think, don't quote me on that. Any questions about how these prefixes work? So units are important. We talked about some basic units. Then there are also some units that are called derived units. These are derived from other units. So many volume units are derived units. Because if you have a block of wood, how do you find the volume of it? You take the length times the width times the height. And what would you measure the length, the width, and the height in? Units of length, right? Like meters or millimeters or centimeters. And so you take that and you cube it, and it becomes, let's see, there's got to be somewhere on this slide I can write. So say you had 2 centimeters times 2 centimeters times 4 centimeters. You had a block of wood, and those were the dimensions. When you do that math, you end up with 16. Centimeters times centimeters times centimeters is centimeters cubed. So 16 centimeters cubed, or cubic centimeters. Do any of you guys watch the doctor shows? I don't watch TV anymore because I don't have time. So I don't even know what the names of them are. I think Grey's Anatomy is one of them. And they'll talk about cc's. Well, give him 5 cc's of this stat, right? cc is the abbreviation that the medical community uses for cubic centimeter. It's a unit of volume. So cc equals cubic centimeters. So cubic centimeters, cubic millimeters, cubic meters, those are all units of volume. Those are derived units. 2 other common units of volume are liter and milliliter. And we use those I want to show you that yet. We use those for volumes of liquids in general. okay? Okay, so that's units. So I love this. How I see math word problems. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? The answer is purple, because aliens don't wear hats. Is that about how some word problems look to some of you? I'm guessing about half of you can really, really relate to that. You're like, yeah, all the way through math, all the way through school, it was always like that, and it was just this big mystery. Okay, that does not mean that you are not as intelligent as people who just magically understand word problems. It means your brain was made to think a different way. Okay, the bad news is that we're going to have a lot of word problems in chemistry. The good news is I'm going to do my best to help you learn how to figure them out so that they don't look like that anymore. So solving a word problem, usually the hard part is getting the equation. If I just handed you the equation and said solve this for x, you'd probably be, okay, great, I can do that. It's taking the words and translating them into the equation. So we're gonna learn how to do that. That requires critical thinking. Okay? It's not going to be obvious to some of you. There's no simple formula I can give you that's going to apply to every problem. What I'm going to try to do is teach you an approach to solving problems that will help you be able to solve all kinds of different problems. You can learn problem-solving strategies, okay? But you have to be willing to learn. I know a lot of people get this math phobia, and maybe it started back in 2nd grade or 3rd grade or something where you just didn't get it and you're like, man, I stink at math. I can't do it. Okay, you have to throw that attitude out. You can do it. It's going to require some work, but you can. So don't give up before you even start. Many problems that we do in chemistry can be thought of as unit conversion problems. Others are going to require specific equations. And so there's those 2 basic types, unit conversion problems and problems requiring equations. So we're going to talk about the unit conversion problems. Units can be multiplied, divided, canceled, just like any other algebraic quantity. So they're a little bit like those variables in algebra. There was A's and B's and X's and Y's. And you had all these equations, 3x plus 4x squared and all those different things. And then you have to combine up all those letters into a neat little package. Okay, so we're going to treat the units just like variables. When we use units as a guide to solving problems, it's called dimensional analysis. The units are the dimensions. The analysis is we're analyzing the dimensions. Probably the most important thing I learned in high school, all of high school, I learned in physics class, and that was dimensional analysis. There are a lot of problems, even if you don't remember the physics equation. If you just put the numbers that they gave you together so that the units cancel out, many times you get the right answer. And it's a useful skill for all kinds of things, even in everyday life. Converting tablespoons to cups, you're multiplying a recipe to feed the football team, all kinds of things like that. You do encounter unit conversions in your everyday life. So it's important to always write every number with its associated unit. Remember that sentence about the little boy throwing and his school. It doesn't make any sense without the units. Do not write down numbers in your work even without the unit. It's got to have a unit. In your calculations, include the units every single time. Yeah, it's annoying, but getting a problem wrong on an exam is more annoying. And don't let those units magically appear or disappear. Okay, there's no magic in chemistry. So treat them like algebraic variables and don't let them just come and go by themselves. So usually what happens in a unit conversion problem is they give us a quantity with a unit and they ask us, well, what would that quantity be in some other unit? Here's a piece of wood and it's 5 meters long. How many centimeters is that? That sort of a problem. So the general pattern for these is this. There's information given and there's information sought. That's what you're seeking. And you're going hate it when it does that. And then you have to avoid touching the screen in the wrong place. So the information given, you're going to multiply by some conversion factor. There may be more than one. The general idea here is whatever the given unit is, we want to divide by that to make it go away. And we want to multiply by the unit that we're seeking so that we end up with the correct unit at the end. So we need a conversion factor to do that. Conversion factors can be made from any two quantities known to be equivalent. So sometimes that'll come from a table like this. This is table 2.3 in your book. You may need to refer to it when you're doing homework problems, and it gives us relationships. 1 kilometer equals 0.6214 miles. These are the sorts of things that you don't necessarily remember all the time because we don't use them very much, and there's only so much room in the brain, right? And sometimes you put something new in, you have to kick something else out. And a lot of these are things that aren't used very often. So it may be something from a table, or you can also make conversion factors using those metric prefixes. Okay, so those are the two main sources of conversion factors. So let's look at how do we make a conversion factor. So we'll think about the English system first because you're more familiar with it. So it's nicer to start with something that's familiar. What is the relationship between feet and inches? 1 foot is how many inches? 12. Okay, that's something that we consider to be basic knowledge. We assume that you know that. So 1 foot equals 12 inches. So whether I call this, piece 1 foot or 12 inches, we all understand that is the same length. We're just giving it a different name, right? My third son, his given name is Thomas. We never call him that. We call him Tommy. But whether I call him Thomas or Tommy, it's the same person I am referring to. Whether I call this length 1 foot or 12 inches, it is the same. It's just a different name. Okay. So now we're going to do a little math here. When you have an equality, something equals something, it's a little bit like a teeter-totter. If you put an extra, let's say you put an 8-pound bowling ball, you've got a teeter-totter with 2 children sitting on it, and it's perfectly balanced. And you give this child an 8-pound bowling ball, and you give that child an 8-pound bowling ball, is it still balanced? It's still balanced because you did the same thing to both sides. With math equations, as long as you do the same thing to both sides, it's still equal. So I'm going to do the same thing to both sides of this. I'm going to divide by 12 inches. You may say, wow, that just seems kind of random. It's still equal, though, because I did the same thing. What is 12 inches over 12 inches? 1. Anything divided by itself is 1. And so we say, well, those cancel out. That equals 1. So 1 foot divided by 12 inches is equal to 1. If I multiply something by 1, does it change the value? No, it doesn't. Okay, so we can multiply by conversion factors, and we're not really changing the length or the mass or anything. We're just changing the units. Now, could I also write 12 inches, that's not a very good inch, 12 inches over 1 foot. Could I do that? Yeah, I could. What is that equal to? That's also equal to 1. In a conversion factor, if you look at what's on the top, 12 inches, and what's on the bottom, those should be equal to each other. Okay, sometimes students get confused and they separate the numbers and they say, well, 1 inch is 12 feet. I get 12 feet per 1 inch. Look at it. Does 12 feet equal 1 inch? No, that's ridiculous. So the top has to equal the bottom. Let's do inches and centimeters. Anybody remember the relationship between those? 1 inch equals 2.54 centimeters. We use that one quite a bit, so that's a good one to remember, but you don't have to remember that one. So what are the two? We can make two conversion factors from this. What are they? 1 inch over 2.54 centimeters, or 2.54 centimeters over 1 inch. Okay, so any equality, so from that table, all those things, this equals that, you can make two conversion factors from every single one of those. Any questions? So, a couple of good ideas for solving these problems. Always check that your final units are correct and that you haven't done anything magical. Okay? You can't say centimeters times centimeters and decide that those cancel out. They don't. Also consider whether the magnitude of the answer makes sense. So your book doesn't give this, but I like this. It's the bigger, smaller rule. And what that means is the bigger unit should have the smaller number, and the smaller unit should have the bigger number. If I take 2 feet and convert it to inches, how many inches is it? It's 24 inches. Inch is a small unit. It has the big number, 24. Foot is the large unit. It's got the small number, 2. And so you can use this as a check on your work. And then remember that conversion factors can be inverted. You can upside down them. They're fractions, and you can just flip them over at will. Because they're equal to 1 and inverting the 1, it's still 1, and you're not really changing anything. So what's helpful is to have a solution map. That's what this book calls them. I've called them paths in other things. But it's a map. You need to know where you're starting, where you're going, and then you have to have a plan for how to get there. Okay? I'm a visual person, and so I like to actually be able to see it, if not on paper, to be able to see it in my mind. Okay, this is where I'm going. For unit conversions, the solution map is going to focus on the units and how to get from one unit to another. So for a problem where we're converting from inches to centimeters, the solution map is very simple. We're going to start with inches, and we're going to go to centimeters. And then in your solution map, identify how do I get from this point to that point. I need a conversion factor. Here it is. If the problem's a little different and you're converting from centimeters to inches, then your solution map is going to look backwards. Because if I'm driving from Reedley to Fresno or from Fresno to Reedley, the path is the same, it's just flipped, starting and ending. And then the conversion factor is just going to be upside down of this one. It's a little bit like crossing a stream. This is a simple conversion problem. You're crossing a narrow stream. I'm on this side of the stream and I want to get to that side. Well, I can just step over. But if the stream is wider and it's not big, I just can't jump that far, then I'm going to have to look and find a stepping stone, and I may have to find several stepping stones to get from one bank to the other bank. So general problem solving strategies, and if you're one of those large number of people who have a hard time with problems like this, refer back to this. These are the steps. First of all, identify the starting point. What did they give me? Did they say, okay, this thing is 537 grams. Convert that to kilograms. Okay, that number is your starting point. Then identify where you're going. There's no point in devising a plan to get somewhere if you don't know where you're going. So you need to identify where you're going, then figure out how to get from where you are to where you want to be. The thing is, to get there, you can only use things that you either know already or things that you can find, that you can look up. Okay? So then you write out your solution map to show how you're going to get there. And so the basic progression here is that we have our given thing, and we're going to use our solution map. Come on, there we go. Solution map to get to what we're trying to find. So we sort the information. The problems that we're going to do in class today are going to be real simple, but sometimes the problems have lots of different numbers in them. And sometimes the writer of the problem is mean and gives you extra information. Don't you hate that? They threw in all these extra numbers that you don't actually need. But pay attention to the numbers in a word problem. Write them down and identify, well, what does this number mean? What is the significance of this number? Because it is going to involve numbers. Then strategize of how you're going to get from the one place to the other. Make your map, solve it, and be sure to pay attention to your units. Okay, let's actually do this, okay? So here, convert 56.0 centimeters to inches. So this is pretty simple. There's only one number, so that's probably where we're starting. So we're starting with centimeters, and then they're asking us to find inches. Some of you may be able to just do these problems. If you struggle with them, write lots of stuff down in the beginning until you get the hang of this. Okay, so we're going from centimeters to inches. What's the conversion factor? Well, you can write it as a conversion factor, or we can also write it down just as an equality that we found somewhere. 1 inch is 2.54 centimeters. That's the information we need to solve this problem. And so then we write down what we're given, 56.0 centimeters, and we're going to have a conversion factor in here. And for every arrow in your solution map, you're going to have a conversion factor. So this one only has one arrow, so we've just got one conversion factor. And then over here, we want to end up with the unit of inches. Now, we're going to use the units. We're going to use the units to figure out what goes on top and what goes on the bottom. So if we look at this path that we decided upon, centimeters to inches, those are the units that go in the numerator, in the top of everything. So here we've got centimeters, we want inches on top over here. We want to multiply by inches because we want to end up having inches left. Centimeters is what we want to divide by because we want these guys to cancel each other out. We want the centimeters to go away. Centimeter divided by centimeter is 1, poof, it's gone. Now we look at our equality here. 1 inch equals 2.54 centimeters. We take those numbers and we fill them in here. In front of inch is the number 1, so it has to stay in front of inch here. And in front of centimeters is 2.54. Now we do the math. 56.0 divided by 2.54 equals. Calculator gives me this big mess. I don't have room there, so I'm going to erase that. 2.20472449 inches. Then we have to think about sig figs. How many significant figures in our starting number? 56.0. 3. How many in that unit conversion? Well, we have 1 inch and 2.54 centimeters. So I would expect an answer of either 1 or 3. A whole number like 1 in a conversion factor is always an exact number. The other number is usually not exact. In this situation it is, but even if we don't recognize that, we'll be okay. We would then say they have both 3, and so this should have 3, and we're going to say 2.20 inches. And we're out of time.